Hey Fizz Kids, Mr. C here, and today we're going to talk about forces at angles, sort of our next discussion about two-dimensional physics. So we already kind of talked about how whenever we look at two-dimensional kinematics, we have to break up our motion into like our x motion and our y motion. So we have to analyze those two differently because they're separate. The same as with forces. We have x force, so we can break up forces into x forces and y forces. I'm going to show you how. Here we have my dog. Not my dog. I would never do this to my dog, but we have three different scenarios here. So in our first scenario, we have only a vertical force. So like our force is just going straight up here whenever we look at that tension. In our second scenario, we have our force all going in the horizontal direction. However, there are times, and more often than not, our forces are going off at an angle. So like in this case, our tension force kind of goes off in the angle. It's not horizontal, it's not vertical. It has some angle. And in this case, this force actually has an x component, and it also has a y component. And we're going to talk about how to sort of find out what that x and y component of our force is. And we're going to find out that it's actually the exact same as if we wanted to find the x component of our velocity or the y component of our velocity. But the big point here is that whenever a force is at an angle, it's not on one of those axes, it's going to contribute to both that horizontal force and the vertical force. So it's no longer just one or just the other. It's going to be a combination. If we wanted to resolve forces on our components, we're going to do it the exact same way that we did whenever we had our velocity was at an angle, or if we had an acceleration at an angle. And we find that this angle here, our force here, has those x components, and it also has that y component. And the way that we're going to do is we're going to use our trig again. So we're going to have some angle here. And in this case, we would find out that the cosine of our angle is equal to whatever our x component of our force is divided by whatever our magnitude is, so force F. So here we have that cosine of theta, which in this case is going to be equal to our adjacent over our hypotenuse, or that Fx over F. And in this case, the sine of theta is going to be equal to opposite over our hypotenuse, or Fy divided by F. And we can actually rearrange these equations to solve for Fx and for Fy. So in this case, like Fx is going to be equal to F times the cosine of theta, and Fy is going to be equal to F times the sine of theta. So we can break this up in the same way that we would break up velocity if we had velocity at an angle that we saw with projectile motion. So we want to use trig to basically break up every force into that force's x component and that force's y component. Okay, so let's talk about solving problems with forces at an angle. And a lot of times forces at an angle is going to include some sort of tension force. So let's say here we have this car with a mass of 1,500 kilograms is being towed at a steady speed by a rope held at a 20-degree angle from the horizontal. A frictional force of 320 newtons opposes the car's motion. What is the tension in the rope, and what is the normal force acting upon the rope? So before we get started with the problems, we have a couple steps. Always, always, always with forces, and I've said this in one-dimensional forces, and I'm going to continue saying this now, and I will say this all throughout the year. You should always draw a free body diagram. Oh boy, that should be FBD. A free body diagram with all of the forces as individual vectors. Do not break them up into components yet. So like in this case, we would want to draw the force body diagram as we have that normal force, we have the force of gravity, we have our frictional force, which in this case is kinetic friction because we're moving, and we would have our tension force at some angle theta there. We don't want to break up any of our forces into components yet. The next thing we want to do is for any force that's not on the x or y axis, we want to split it up into its components using our trig, or that SOHCAHTOA. And finally, as before, we're going to write two different force equations, one for the x-axis and one for the y-axis. And using this problem here, I'll do other example problems. I'm going to show you what that looks like. So I already drew that force body diagram. So like here we have that our normal force, we have our force of gravity, we have our force of friction, and we have our force of tension there at some angle theta to the x-axis. So that's part here is checked. The next thing is we want to break up our forces into x and y components if they don't lie on an axis. So like in this case, our normal force lies on an axis, our frictional force lies on that x-axis, and the force of gravity lies on the y-axis. So the only one that is at an angle to the axis is actually our force of tension. So we want to break that force of tension up into different components. And basically, using our angle here, we're going to use sine and cosine, and we know that the sine of theta is equal to the opposite over the hypotenuse, which in this case is going to be that y portion of our tension force divided by our tension, or Fty is going to be equal to the force of tension times the sine of theta. And if we look at cosine of theta, we know that's equal to the adjacent side over the hypotenuse, or in this case, if we look at our diagram, that'll be Ftx divided by Ft. And we can rearrange that and we find that Ftx is equal to Ft sine of theta. The next thing we want to do is we want to write those F net equations for x and for y. So like F net x is going to equal to all of the sum of the forces in the x direction, which in this case is going to be that Ft times the sine, or Ftx minus the frictional force, or Ft times the Ft times the cosine of theta minus our frictional force. And F net in the y direction is going to equal to the sum of the forces in the y direction, which is going to be that Fty plus Fn minus Fg, or Ft sine of theta plus the normal force minus the force of gravity. So that's what our two force equations are going to look like here. The next thing we need to do is we want to solve for what our force of tension is and what our normal force is. So back from there, we know that F net x is just equal to that Ft times the cosine of theta minus my frictional force. And I know that F net in the y direction is equal to Ft sine of theta plus my normal force minus my force of gravity. And because we're moving at a constant velocity, as it said earlier in the problem, anytime we move at constant velocity, we know our net force is just equal to 0. So if I look here, I can actually say, so I know my frictional force, and because I know my angle, I can actually solve for my force of tension. So here, if I rearrange my F net x equation, I can see that Ft cosine of theta is going to be equal to my frictional force, or that force of tension is going to be equal to my frictional force divided by the cosine of theta. You can go ahead and put that in, plug that in. We have 320 newtons is our frictional force divided by the cosine of 20 degrees is going to give us what our frictional force is. And I'll go ahead and let you plug that into your calculator because I don't have mine with me right now. So we already know what my frictional or what my tension force is. So that's good. So the next thing I want to do is I want to find my normal force. And I actually have to use the F net y equation. So if I look at this, I have that Ft sine of theta plus my normal force is going to be equal to the force of gravity because I can add that force of gravity over. And then I find that my normal force is equal to the force of gravity minus my tension force times the sine of theta, which is going to be equal to my force of gravity is just mg minus that force of tension we already found is that force of friction divided by the cosine of theta times the sine of theta. We can go ahead and plug in our numbers, and we have that 1,500 kilograms times 9.8 minus my frictional force of 320 newtons divided by the cosine of 20 times the sine of 20 is going to give you what that normal force is here. Notice here that our normal force, in this case, is going to be less than what our weight is. And that's because that tensional force is also pulling up too. So in order to have a balanced force, the force of tension plus the weight or the force of gravity must be equal to the force, the normal force. So my other question here is, how would this be different if the car was accelerating? Well, if the car is accelerating, let's say in this case we're only accelerating the x direction. The way I would write my f net x equation is I'd say f net x is equal to that ft cosine of theta minus that frictional force, and instead of equaling it to 0, I would say it's really equal to mass times acceleration. So remember, anytime we're accelerating, our net force should be equal to mass times acceleration. But because we're only accelerating in the x direction, our net force in the y would actually be the exact same equation. So we'd still have that ft sine of theta plus the normal force minus the force of gravity is going to be equal to 0. So make sure you keep those straight and you know what direction we're accelerating. If we're accelerating in the x direction, f net x is equal to mass times acceleration, and if we're accelerating in the y direction, f net y is going to be equal to our acceleration. So here's a quick check for you, and this is actually going to be one of the learning check questions. So never mind, I just gave you the answer on accident. So in this one, we want to know, so we have 2 of the 3 forces are shown right here. So we have force 1 and force 2. But we know that we're accelerating to the left. So basically what we need to do is we need to pick a vector or a force vector that would cancel out this, this vertical component here and this rightward component here so that our overall net force was to the left. And in this case, it's going to be that vector c, which points down here, because as we can see, this component here will cancel out with force 1, and part of my x component will cancel out with force 2. I'm going to talk more about this in class and how we can add forces together. The next problem I want to work out, and I'll do this kind of fast, and we're going to go over more tension problems. But we have a sign that weighs 200 newtons that is hanging at rest from these 2 ropes attached to the wall, and we want to find what the tension is in both of the ropes. So the first thing I'm going to do is we're going to draw that free body diagram. So we have our force of gravity, which points down. We have one tension force, that force of tension B, which is pointing off to the side like that. And we have our force of tension A, which makes an angle of 40 degrees here to the ceiling. So what do I do next? Well, now I have to basically break up any vectors that are at an angle. So in this case, my force of tension in B is all in the x direction, and my force of gravity is all in the y direction. So the only one I have to break up into components is that force of tension of A. So using my sine and cosine, I know that the sine of theta is equal to opposite over hypotenuse, or in this case, the opposite side of this 40 degrees is going to be my y force. So that's going to be equal to y over, or FTAY over FTA. And my cosine of theta is equal to my adjacent over my hypotenuse, or in this case, the x component of my tension force in A. So FTAX over FTA, or FTAY is equal to FTA times the sine of theta, and FTAX is going to be equal to my force of tension in that rope A times the cosine of theta. The next thing I want to do is I want to write out my F net equations in the x and the y direction. So F net, the x direction, is just going to be equal to my forces in the x direction, which in this case is going to be that FTA in the x direction minus FTB, or FTA times the cosine of theta minus FTB. And in the y direction, I know that my net force is going to be equal to FTAY minus my force of gravity, or FTA sine of theta minus the force of gravity. And both of these, because we're hanging at rest, we're not accelerating, are going to be equal to 0. So I basically want to solve for what the tension in both ropes are. And I'm going to look here and I see, well, in my F net y equation, I only have one tension of one of the ropes. I know what my angle is, and I know what the force of gravity is. So if I rearrange that equation, I get that FTA times the cosine of theta has to be equal to FG, or FTA is equal to Fg over the cosine of theta. And if I plug in my values here, my force of gravity is this 200 newtons. So I'd have 200 newtons all divided by the cosine of 40 degrees. And that's going to give me my force of tension in the rope A. And then what I'm going to do is I'm going to look at my F net x equation, and I see that, okay, well, FTA times the cosine of theta is really equal to FTB. Or FTB is equal to, if I plug in from before, that Fg times the cosine of theta. Oh, sorry, this is supposed to be the sine of theta. FTB all divided by the sine of theta. And that's going to give me what my force of tension in the rope B will be. And I'm going to go over this one in class again, and I'm going to talk more about tension because tension is the most confusing. Right now, I do want you to go and I want you to answer that video check about this video. And I will see you in class, and we will talk more about forces in 2 dimensions.